Micah DeCleene, and this is my artificial blood vessel, primarily focusing on the ascending aorta. So the ascending aorta is found right here. It's very central to your body. It's this ginormous vessel right here that almost covers the entire length of your body. So it starts right here from the heart. It goes into this ascending aorta right here, into the arch, and then to the descending aorta. A cool thing about it is that it is a huge hub, and it leads to other organs in your body right here. And then it goes down into your two legs. So the three primary parts of the aorta is right here, which is the ascending aorta, this arch up here, and then the descending right down here. And as you can tell, it's a huge part of your body and a large component that carries blood from the heart away into the rest of your body. So these are some dimensions on an average male around the age of 20 to 40 years old for the ascending aorta. So the common inner diameter is about 2.91 centimeters, give or take 0.4 centimeters. The thickness of wall in this blood vessel is about 0.16 centimeters. The flow rate is 87.5 milliliters per second. The flow rate at 5 times the average flow rate is 707.72 milliliters per second. The velocity is 0.11 meters per second. 5 times the average velocity is 0.55 meters per second. And through the SolidWorks simulation, we used a healthy blood pressure of about 16,000 pascals. So these are the three types of materials used through the SolidWorks simulations. There's PET, PVAL, PTFE. All the scientific names are found right next to it. PET is a common hard, stiff material that is used in a lot of biochemical components. It's stable, and it also is very biocompatible and is used in medical devices today. PVAL is probably most common and heard of. It is used in cosmetics such as makeup, foundation that girls use, along with surgery that happens in your face. You usually use this PVAL as a component. There's PTFE, which is used for coating materials to give a non-stick effect to them. So this is the materials at each of their cost per pound. These costs were found for America specifically. So as you can tell, the PET is cheapest compared to all three, pretty significant, and then the citations are found in the references at the end. These are the SolidWorks drawings that were completed for all three materials at 3 different lengths. So the only difference is that the material was used and selected in SolidWorks, but the dimensions are all the same. The thickness is all the same. However, the length of each vessel is all different, as you can tell. So this is for 1 millimeter of length, 10 millimeters of length, and then 100 millimeters in length. This is the flow simulation for just the PET at a normal flow rate. As you can tell, all three remain pretty consistent around the 16,000 pascals. Then again, it's also for the PET, just to save time. So as you can tell, the flow rate remains pretty constant, showing that the walls in this vessel do remain stable through the process of the simulation. This flow simulation demonstrates the PET at 5 times the normal flow rate. And as you can tell, there's still a consistency and showing that the walls will remain sturdy if in case 5 times the normal flow rate. These are results for all three materials, PET, PVAL, and PTFE, all showing stability through all flow simulations, showing great results that these materials will work within the human body of a male. This is the stress and strain analysis, as you can tell through all three materials. As stress increases, so does strain, showing a proportional relationship. This stress and strain was calculated from the stress that was gathered through the simulation in SolidWorks, and then by using the elasticity that was found in each material. This analysis was performed to find the strain. So through all the process of elimination, the best choice for the artificial blood vessel is in fact the PET, based on the price purely. All three simulations showed similarity in outcome of pressure impacting the walls for both normal and 5 times the pressure. However, due to the price differences, PET is the best choice of method for the blood vessel. Other key components for going along with this material is the biocompatibility. It meets engineering standards along with being FDA approved, already easier to use, skipping a few steps along the way to go ahead and build a blood vessel that is made from this material. And this is my list of references. All right, thank you, goodbye.